So welcome. This is the first of 4 webinars on LHPs. Today's webinar is going to focus mostly on LHP components and phenomena, and not so much on the modeling at all. And then the next 3 webinars will talk more specifically about the modeling aspects. And it's a fairly ambitious agenda here today because we'd like to talk about just a quick overview of cycle level operation of an LHP. And this is the sort of thing that you probably already know or that you can find easily online. So I'm not going to spend a lot of time on that so much as the more interesting things that can happen inside of an LHP that you may not have heard about or might not easily find information online. So we're going to talk about all the different components of an LHP, starting with the simplest one, the condenser, and then getting into evaporators, condensation chambers, bayonets, secondary wicks, and so forth. Then we're going to talk about the transient phenomena that can go on here with things like thermostatic control and oscillations and startup and flooding during gravity assist operation. And then wrap up with some talk about what happens when you have multiple LHPs in parallel. And as I mentioned, this is really the start of a 4-webinar series. This webinar is intended to give you an overview of the kind of things that you should look out for in an LHP, but then we'll be talking about a system level modeling early next week. Jane will be leading that one, and she'll follow that up with another webinar that's more specifically about back-conduction. So you're going to hear a lot about back-conduction, both in the talk today and in Jane's 2 webinars next week. And that's because it is a fairly important concept to understand in LHPs and an easy one to basically get wrong. So apologize if that seems to be a little bit redundant, but after you've heard enough, maybe it'll start to sink in. Advanced LHP modeling will be the final and 4th in the webinar series. Of course, these next 3 are all about modeling, and the first one is more about components and phenomena. So after I wrote this this webinar up, I realized it was just a kind of a drink from a fire hose. There's a lot of material here. It's going to be very easy for you to get overloaded and overwhelmed and think that, oh my gosh, these things are too complex. I don't understand at all what's going on. So I just wanted to warn you that the purpose today is really to try to show you some of the interesting and different things that can happen, but don't get too concerned about it. We're going to show the basic workings, of course, but we're also going to show you some things that are fairly unusual. And you, if you're an LHP user, may never even encounter these, but it just seems more honest to make sure you know that they exist, because I think it's very important for you to know that they might happen. And I'd also like to point out that maybe something is going to happen in your LHP that we didn't mention. So please don't let this be the end of your research on LHPs. Make sure you do your own due diligence and study what other things you can find out there in the literature or from talking to experts. It is kind of a concern or opinion of Jane and I that there's a fairly good knowledge gap between the manufacturers of LHPs and the integrators, basically the people who make them and the people who use them. And too often, it's easy to think of an LHP as kind of a black box and hope that everything works out. And so the folks who make them may understand some of the funny things that happen inside of them, but not convey it or not think it's a concern. The folks who use it may not realize what they're doing that might stress out an LHP. So one of the purposes of this talk is to try to kind of heighten that awareness that there's a lot that can go on here, and that a really successful mission is one in which there's really good communication between those 2 teams, the people making them, supplying them, and the people integrating, testing, and making sure that they work under all possible scenarios. The other thing, I guess, is a bit of a waiver, but what I'm going to present is, of course, Jane's and my view. This is how we think the things that are important and that can happen. But it's certainly, the LHP community is diverse and has a lot of diverse views. I looked through the list of people who have signed up for this, and I can see several people who probably know a lot more about LHPs than I do. So once again, just a little bit of a waiver or caution that this is not the last word. This is just something that you should consider and should think about. and that you should also look for other viewpoints and other opinions on it, which is a polite way of saying that I've probably muted out some people here who might disagree with me. The purpose of this presentation, why we're giving you this overload, is basically to help you to learn how to begin to model LHPs at a top level, which is the next webinar, but also to make sure you understand what a top level representation, a system level model is missing, what kind of things could happen that won't happen in your model. So if you make a system level model and everything works great, doesn't mean that the LHP will work great, that you may have missed something. So we're going to try to peel back the layers of the onion here and show you some of the other things that can go on and how to deal with them, including at a more detailed level. And the purpose, of course, is so that you can decide what level is appropriate to focus on and hopefully intelligently neglect anything that you don't think is relevant or going to happen. So we have to get back to the basic LHP, of course, which you've probably seen diagrams like this before we even signed up for a webinar like this. This is from our friends at ACT. And at its heart, an LHP is got this fairly complex looking evaporator condensation chamber assembly. But let's start here at this nice simple tubing with saturated vapor coming out through the system, gradually condensing, maybe some point around here, completely condensing, and then being all liquid maybe in the last part of this condenser, and subcooling a little bit and returning back into this assembly that we'll be talking a lot more about, the compensation chamber evaporator assembly, where all the vaporization and interesting things happen. The compensation chamber, by the way, I will be abbreviating a lot as the CC, because it's just difficult to carry around a term like compensation chamber over and over again. So now that I've introduced the basic diagram, which again I think would be no surprise to anyone attending this, if that is a surprise, I don't know why you signed up for an LHP webinar, but now you've seen what the basics are. Let me talk a little bit about the pros and cons, and again, this is our viewpoint. They are usually self-starting. Usually you apply the heat, it goes. It balances power in and out, so if you have 100 watts going in, 100 watts will come out, which is, I guess, an energetic way of saying that it's working, because if 100 watts went in and nothing came out, it's not working. It's also easy to add heaters for tighter thermostatic control, so it isn't just floating in set point, you're actually regulating the set point it's operating at. And of course, probably the #1 reason LHPs are popular is that they have no moving parts. Add heat here, it comes out over there at a fairly good distance and a fairly good rate. But to me, I think that misses the point of one of the beauties of an LHP, is that it consists so much of just simple, plain, and in fact small diameter tubing. And that means you can accommodate just regular plumbing like flex joints or disconnects and manifold things, and put in T's and all sorts of things that you just couldn't do in a traditional heat pipe. And that also allows you to have really tight thermal integration in some of these components. You can have an evaporator that's bonded in tightly to the application, and then a condenser that's designed and integrated separately, and then hook them up later at a higher level of assembly. And of course, that's also something you just can't do in a traditional heat pipe. The other pro of an LHP is this is definitely proven technology. This has been around for years, many success stories. Right now, above our heads, there are many LHPs up and working in satellites. The cons are that it's not quite as simple as some people think they are, that sometimes they stall out at low powers, and if you have a large attached mass, the thing you're cooling is heavy, which is almost always true. Then when you apply heat and this thing starts to dissipate, you inevitably go through a low power regime, and that's a little bit of a danger zone for an LHP. Even if it does start successfully, you can get some temperature overshoots starting or during startup, so that it starts, but it did so by going to a temporarily high temperature that you may find disturbing or that violates your design requirements. Another potential negative to them is that they are easy to regulate, but it can require fairly large heaters to do so. So the thermostatic control of them can come at a price. We'll talk a lot more about those things later. The other thing that is a con is, like I say, they're not really this simple black box where you put in heat and out it comes and you don't have to care about what's happening inside of them. They do exhibit hysteresis, and there are some fundamental uncertainties in what's going to happen, how it works, and what will happen when you turn on heat the next time. And just as a brief example of that, horizontal is not the same thing as microgravity. Of course, that's not quite true for a traditional heat pipe either, but it's even more true for an LHP, that just because you've tested something in a horizontal position doesn't mean it's going to operate exactly like that in microgravity. Things like secondary wick performance and the positioning of liquid in the condensation chamber and other things that I don't want to explain right now can cause it to be a different behavior in each case. So just an example of the kind of uncertainties that come about that you just won't find if you treat this thing as a black box. So in order to have a successful program, you really need to have detailed knowledge and participation from both the vendor, supplier, manufacturer, and the user integrator of this system. They're rarely the same company or organization. So that requires you to go out of your way to make sure there's good information exchange between those two organizations. And that's something that Jane and I are perpetually concerned about. It does require you to have specialized analysis tools too. These are specialized devices. They aren't amenable to simple first order analyses in any stretch of the imagination. And it also means that you have to know enough about what's happening to intelligently apply design margins to overcome some of these uncertainties or hysteresis inside the system. So let me just talk a little bit about the sensitivity to orientation. This is kind of a broad brush. There's a lot we're going to talk about later, but just to give you a rough feel of what's happening here is that at high powers, an LHP is roughly a constant conductance device or fixed conductance, and it's not as sensitive to orientation at high powers. So if I were to plot a curve here, you've probably seen curves like this before. We're going from low to high power on this axis and looking at the total temperature of the evaporator, which is an indication of the delta T for the system. You would see that at high power, it really doesn't matter whether it's upside down or right side up and so forth, but at low power, the 2 points start to diverge and become more sensitive to orientation. Understanding this is going to be something we're going to keep coming back again and again to. So if you don't quite understand what I'm about to say, don't worry, we're gonna repeat that conversation several times. So this condition here of the evaporator above condenser that corresponds to this red line is called adverse elevation or adverse tilt, which is kind of a borrowed term from the heat pipe world. But either way, it means that the gravity is fighting you, that the wick inside the LHP has to overcome both the pressure drop in the loop and the hydrostatic head of gravity. And because of that, at low power, the loop conductance decreases right here. So this is what we have to explain here, is why does this happen? And we'll be talking a lot more about that later, but I also want to mention that since we're talking about sensitivity to orientations here, that if you invert it and have the condenser above the evaporator, now gravity is helping. It's now helping you circulate, but it can help so much that it essentially no longer becomes an LHP, it becomes a loop thermosiphon, an LTS. And in that case, it's easy to lose thermostatic control because you're getting actually a lot more flow than you thought might happen if you hadn't planned on it. Since we're on the subject of orientation sensitivity in general, for reasons I won't go elaborate on here, you are going to want your evaporator condensation chamber assembly to stay roughly horizontal. So you have to understand these kind of limitations and effects when you're planning out ground testing of a spacecraft, for example. Okay, so let's talk a little deeper pass of what's happening of that sensitivity to tilt and sensitivity to liquid line heating. And to me, it helps to think of an LHP as a transistor, meaning that a little heating of the liquid results in a big change in the heat flowing through the loop or the loop conductance. So to explain this, let's first of all consider an evaporator that has 100 watts going into it. Okay, 100 watts being dissipated out of your equipment. Most of that will be vaporized, but not all of it. Let's just say for right now it's 95% of the heat coming in results in vaporization, and that means that the flow rate through your loop is roughly 95 watts divided by the heat of vaporization of your working fluid. And of course, the heat of vaporization is a very big number, so this is a very small flow rate, and that's definitely a feature of loop heat pipe, is it doesn't take much flow rate to transport a lot of heat. But not all the power got vaporized, so what happened to the rest of it? Well, it's that back-conduction term that if it didn't get vaporized, then it leaked back into the inside of the wick, and what you might call the wrong side. And so 95% say, these are just rough numbers for talking, this isn't typical, but let's say that 95% of the power ended up on the outside or the right side of the wick, and 5% ended up on the wrong side or the inside of the wick. In addition to that, you're going to have other things like maybe intentional heating or heat leaks on the compensation chamber. As you saw, the evaporator and the compensation chamber are right next to each other, so it's pretty easy for heat to leak over in this nice hot zone into a zone you don't particularly want to heat. And of course, other sources of environmental leaks. Just to be generous, we're going to say these are very small, 1 or 2 watts. Just for talking purposes, what this does energetically in the loop is it means that the condenser has to be rejecting that 100 watts plus these two terms here that came in from the side for a total of 103 watts. But the condenser has to produce enough subcooling to offset these blue terms, these heat leaks, this 5 watt back conduction plus the heat leak into the compensation chamber and the environmental. Anything that did not go on the right side of the wick basically has to be overcome by subcooling. And if we were to take that 8 watts and divide it by the mass flow rate times the specific heat, remembering that the mass flow rate is pretty small here, then you get, if we were to take an example of just ammonia at 20C, very, very small flow rate, as you can see, but a fairly large subcooling to combat that 8 watts of heat leak. And so the condenser not only has to get rid of 103 watts of heat, it has to produce 21 degrees C of subcooling for the loop to balance. So if you were to consider this to be like an overall conductance of the loop, 100 watts total divided by 21 watts delta T, you can use that as a figure of merit for the conduction of the loop. But it's a little bit pessimistic to do that because most of the energy actually was rejected at a much higher temperature. Nonetheless, if you had a fixed sink temperature, you had to reject at a fixed temperature, that puts a minimum delta T on the whole system because of these heat leak terms. Okay. If this did not make sense, don't worry. This is the first of many passes. We'll be back to this subject over and over again. But for right now, in terms of understanding sizing and how an LHP works, that sensitivity to minor heat leaks, that transistor effect, means that it's pretty easy to control the temperature of a cooled component. Instead of letting it just drift with a fixed conductance or constant conductance LHP, you can add a little bit of heat to regulate it. And in fact, you can add a little bit of cooling to pull some of the heat off of it, such as a thermoelectric or Peltier element to achieve slight cooling. And we'll talk a little bit more about why you'd want to do that later. But I want to make the point that easy is not necessarily cheap, that it's very easy to apply heat, but you may have to apply a lot of it. And so we'll talk a little bit more about that in a couple of slides, but for right now, it may take a lot of heat to overcome that, that subcooling in a very cold environment. So I think it's useful to talk about the different kinds of ways in which those blue terms in the prior sheet can come into it. They can be intentional, incidental, or unavoidable. So intentional is here. I'm applying thermostatic control to achieve temperature control in my payload. So that's intentional, but there's also some incidental, such as warming of the liquid line. Sometimes that's actually intentional, but often that's just a result of your design. Also remember that the evaporator and compensation chamber, as we'll show later, are very tightly linked. So it's easy for heat to kind of leak over into the compensation chamber from your cooled structure. But there is an unavoidable term here, and that's the heat leak back through the wick itself, or back conduction. Once again, that term showing up again, just to show you why that's of importance, because even if you were to do a perfect job on the rest of these terms, back conduction will always be there to greet you. So we'll get back to that over and over again, but for right now, let's go back to condensers to talk about some of these subcooling requirements. Good news about condensers is they're easy to design. It's usually just a plain tube, often a very small diameter tube. You can arrange it however you want inside of a plate or inside of a heat sink. You can have parallel passages and so forth. And this is an example of one condenser. This is a radiator, so it's a radiative environment off of this condenser. And this is from a particular design that transports the vapor line over. So this is not actually connecting to the condenser plate until this point. At this point, it starts to serpentine back, condensing until finally it gets very cold and then comes back and actually reheats a little bit before it exits. And something else that's going on over here is that there's a separate subcooler. So what's going on here is that this little piece of radiator is unattached thermally to the rest of the plate. So in case this plate gets warm, at least this little piece is still providing the subcooling that you need as a minimum in a warm environment. But we have kind of an intentional regenerator effect going on here, where we bring the hot vapor in and counterflow it very close to the liquid line intentionally, so that you don't spend too much power trying to reheat that cold fluid when it comes back in. So that penalty for thermostatic control is reduced. That's almost easier to show inside an analysis. Here's the hot vapor line coming over and then serpentining back and forth, getting to be very cold, coming back and reheating against the incoming vapor until it leaves as slightly subcooled liquid. So a condenser is very easy to model, no complex concepts. You just have to be very detailed about it in how it's laid out, in conduction and contact and those sort of things. And of course, radiative environment. Now, they're easy to model with one exception. What if you had multiple condensers and they didn't all see the same sink? What if they saw different rejection conditions, different sink temperatures? In that case, an example would be, say, a spacecraft where you have different radiators on different panels, and occasionally one might be in the sun and one might be in the shadow, and you, of course, want the side that's in the shadow to be condensing and the side that's in the sun or earth-facing to be turned off. And it turns out that's not difficult to achieve thanks to a thing called a capillary flow regulator, which also goes by other names. And here's again from ACT a diagram that they nicely provided of such a device. What's going on here is you've got flow coming in from one condenser here and another condenser here. And if they're both flowing liquid, great. Liquid goes through these capillary barriers here and flows right out back to the evaporator condensation chamber assembly. But what happens if this one, say, is hot and it's not condensing completely? You will get bubbles coming up here, but they hit this barrier and stop. And in fact, if you have enough of them, it will stop the flow totally there and turn off or ignore a hot side passively. Again, no moving parts, no computers, no control, just passively works. So I just want to mention that. And in fact, this is the one time I will actually talk about modeling. The rest of this webinar doesn't really talk about modeling, but since we don't have a lot of notes and models on a flow regulator, just make a few notes in case you are a Thermal Desktop FloCAD modeler. This is how you might approach them. So let's get back to evaporators now. This is obviously where it becomes a lot more interesting. This is a diagram from someone's paper. This is kind of a cartoonish diagram. This is not what they really look like, but it's close enough for us to talk about them. There are all sorts of variations of what's going on inside these, and for our purposes, we don't really care. We're really concerned with a primary wick here that does the pumping, and we're concerned with the secondary wick, whose job it is to take liquid to the primary wick, and a bayonet, which comes in and supplies liquid here. at the dead end of the evaporator, and of course passing through the condensation chamber on the way. So we're going to talk about this in a few different diagrams later, what exactly the bayonet and secondary wick are doing here. But for right now, I just want to point out that the primary wick is generally going to be a sintered metal wick. We're generally talking about pore sizes of 1 to 2 microns, so it can do a fair bit of pumping. And the secondary wick is going to have a lot coarser pore size. Its job is really just to get liquid to this fine pore wick, so it doesn't have to do as much work. It's not pumping the whole loop. But for this primary wick, we want low conductivity wicks. So sintered metal is fine, but not copper or aluminum. We want to use titanium or stainless steel or something that doesn't have much conductivity in it. Why is that the case? Good old back conduction again. Remembering that LHPs are sensitive to that heat leak into the line, and that some of it, if you recall, was unavoidable. So let's talk about that unavoidable heat leak just a little bit more. Yet another pass back to the same subject. That heat that goes backwards into the wick against the outwardly flowing liquid is essentially the same term as intentionally heating the condensation chamber or heat leaks into the liquid line. It all does the same thing. Any of those heat leaks have to be counterbalanced with subcooling, like I showed on that previous chart. And that, of course, means lower conductivity of the entire device, because the condenser is essentially blocked with liquid, not doing a whole lot of heat exchange for an overall minimum delta T for the whole system. And again, that's pointing to this region here. But even down here, this flattening is also caused by back conduction too. So even if you got rid of all these other heat leaks, you'd still have backward conduction through the wick. Why? Because the delta P that makes the LHP flow in the first place creates a delta T. There are two saturation conditions, one on the outside of the wick, one on the inside of the condensation chamber. So thanks to good old Clausius Clapeyron, there's a delta P. If there's a delta P across the wick, there's also a delta T. If there's a delta T, there is back conduction. There is a hotter temperature on the outside than the inside, and so you have to create subcooling to fight that. Now, if you had an elevation difference, that adverse tilt that's happening here, this delta P is not just the delta P to cause circulation in the loop, it's also that hydrostatic term. So this delta P is larger, and so that creates a bigger delta T across the wick. And yet, thanks to the elevation difference, that delta P is not being spent circulating more fluid. You actually have less fluid to work around. So that causes an even greater subcooling requirement in the whole system. And Jane is going to hit that term again. So again, if this is a little bit of overload, don't worry about it. We'll be back to these. One thing that Jane will also be talking about is uncertainties in the evaporator core state. Just quickly, there's about 3 different kind of conditions you can get inside the evaporator wick, on the wrong side, if you will, on the inside term. One is what you might call a nominal condition. It's slightly subcooled liquid. And that might be what you call nominal back conduction, but it's possible to have two-phase fluid inside the core, sometimes inside the wick itself, but also bubbles and so forth inside the core. And that causes what's called an augmented core or an augmented back conduction. So it actually results in even more back conduction than you would get in this situation. Just thinking of it like almost solid conduction, it's like solid conduction plus. I'm not going to talk about why that happens, but just so you know that it happens and that you have to cover that condition analytically. This is really pretty rare, but it's actually been seen. It is possible to get metastable superheated liquid in the core, liquid that failed to boil, basically, liquid that just stayed hot and got above the saturation condition, but just didn't boil. If that happens, that's like a minimum back conduction case. It means that there is no heat leak back into the wick because the inside of the wick became hot and stopped the heat from coming back into it. Now, favorable is in quotes here because it isn't favorable if you can't count on it. If this happened all the time, great. An LHP would have very high conductance all the time. but it doesn't happen all the time. In fact, it's pretty rare. And when it does convert back to a stable state, it does so by flashing into two-phase fluid fairly violently, and it can take you right back to this condition of two-phase fluid inside the core. That's not the only reason you get two-phase fluid in the core, but it's definitely one of them. But the reason that we want to pay attention to it as designers is that if it is favorable and it does happen, it may mean you have to size your heater accordingly. If this were to happen in your system and your heater was not big enough, you may lose control and your payload would start to cool down in a very cold environment. So it's just one of those conditions you have to design against and bracket. Again, Jane will talk more about that in the upcoming webinars. Okay. All right, over to the compensation chamber. Another name for that is of course a reservoir, which is kind of a CPL term. A hydroaccumulator is another term that was used in the original literature, but I think more and more we're seeing just compensation chamber or CC. The purpose of this is to cover changes in liquid volume. As you heat up liquid, of course, it takes up more volume, and so you have to be able to handle not just operation cases, but things like non-op transport in a hot environment. You want to make sure that your whole LHP doesn't hard fill with liquid, because then the next step is rupture. So this is that void space here, but what's interesting about a compensation chamber is it is always tightly linked with the evaporator. So we're going to talk more about that in this cold fluid coming in here. This secondary wick zone here that's connected, that connects the compensation chamber with the primary wick. And in fact, because they are almost always co-located and they have that secondary wick connection, thermodynamically or energy-wise, it's actually better to think of this zone over here, the secondary wick zone, is actually the same as the inside of the compensation chamber. So when we have a delta T across the wick, it's not just a delta T from here to here, it's essentially delta T from here to here. So again, it's kind of like the connection between the compensation chamber and the secondary wick core state is tighter than you might think, even though they're spatially separate from each other. And just to make things even more complicated, there can also be tertiary wicks, things that help position and carry liquid from the compensation chamber over to the secondary wick, which then carries it to the primary wick. I'm not going to cover a lot about that other than to mention that those happen. I do want to talk more about secondary wicks, though. The purpose, as I said, is to make sure that liquid is always has a way to get to that primary wick, that even if the core is dry, even if there's no liquid inside the core, that the wicking action of the secondary wick can help get liquid over there to keep the primary wick flowing. So it's kind of like a heat pipe-like connection between the core and the compensation chamber, because it tends to be a fairly porous, low, large pore size wick. You can't orient it at any old orientation, either by pooling or by secondary wick action. You have to be able to make sure that primary wick stays wet. So let's take a diagram here. We're going to take a cutaway through here. So this is the vapor channel, this is an artery or the core, and this red is the secondary wick. So taking a slice through that direction, let's say that this is dry, that there is no liquid inside that artery. The purpose of the secondary wick is to basically take liquid from the compensation chamber, perhaps because of those tertiary wicks, get it down the length, very low flow resistance hopefully, get down to here and then have it wick out through the primary wick. So it doesn't matter if this is dry and not supplying any vapor for whatever reason, the secondary wick can help jump in there and take over the load and get the fluid over to the primary wick. Bayonets, we're gonna, if you notice me going back and forth here, I just rotated the cutaway here from there to there. So now I'm taking a slice through the artery. So this core state here, which I said is best off considered as part of the compensation chamber. In this case, I'm going to look at the function of the bayonet. So what if the secondary wick isn't supplying liquid? What if the bayonet is? So now I've got liquid coming in through here, being deposited at this dead end, and then flowing backwards. So my diagram is a little defective here because there should be a line right here, I guess, to depict a dead end. nonetheless a fairly high flow rate of cold liquid that's coming in that you don't want to mix directly with the vapor inside here. You mostly want this nice cold liquid to, instead of collapsing this state here, you want it to help cool the secondary wick and the core. Okay, so it's easiest to see this by watching liquid come in, come all the way to the end of this, turn around, and then go backwards out the outside, filling up these channels here. And of course, once again, the primary wick is happy because it's got liquid on the inside. But in this case, unlike the secondary wick case, liquid is coming in, it's pushing out whatever was inside here, helping to keep it cold at the same time. So this point over here is kind of a stagnation point, because by the time the liquid gets all the way over here, it's done its job and is being pulled out by the primary wick. However, I'll talk later, there are some oscillation mechanisms that happen where you get oscillation going back and forth between this flow in here and the condensation chamber. So now it's oscillating back and forth inside the artery. But before we talk about that, I want to talk about thermostatic control. Remember, we can add a little heat onto the condensation chamber to turn down excess loop conductance and keep something from getting too cold, a lot like a BCHP does. Otherwise, an LHP's temperature would passively float to achieve the power balance. And as I mentioned before, in a cold environment, that can take a lot of power, which no one wants to spend on an LHP. Now, there have been, over the years, many means of lowering that power requirement that have been proposed and tested. I think it's a little bit funny that people are not hesitant to add back moving parts into something whose primary benefit was no moving parts, but nonetheless, that shows you a little bit of the kind of desperation to try to figure out how to keep that heater power requirement from getting too large in a very cold environment. But more commonly, you end up working with a recuperative exchange like I was showing you in that previous radiator, where you try to take the vapor and liquid lines and interconnect them intelligently, not too much, just enough, so that you don't have so much subcooling coming back again that you have to overcome. But just the same way you can apply heat on the condensation chamber, you can apply cooling. I mentioned that before. And that actually increases loop conductance instead of decreases it. And it also turns out to be a nice companion to an LHP because it also can help on startup, as I'll show in a minute. But before we talk about that, I want to talk about the sensitivity that you may not be aware of to thermostatic control. Remembering that this LHP is kind of like a transistor. That means that slight changes in the heater power you apply to the CC can result in large changes in the transported power through the LHP. And that's important to know because you have to size on peak, not average power. So to show you an example of that, here's an LHP. This is, again, I think, analysis, not test, but this is an LHP oscillating between 170 watts and 225 watts. So the average might be about 200 watts. But you have to design for a peak of like 225 just because just the thermostatic control alone is enough to cause the LHP to turn on and off by quite a bit. In this particular case, there was 11 watts of heater on causing that swing from 170 to 225. And again, this is especially acute if you were attaching the LHP to a large mass. I don't want to cover the condenser condensation chamber oscillations too much because they're not really a critical issue, but I just want to mention that they exist. So I'm, in the interest of catching back up on time here, I'm going to just jump ahead and show that connection here. I haven't even shown the bayonet. It looks like the bayonet's not even there. But because there is high resistance of flow resistance here on the vapor side, low resistance here, because there's a fairly stiff liquid vapor interface here, but a fairly loose or flexible one over here, it's pretty easy to see why oscillations would be going back and forth here. And I'm not even sure you need to be aware of them. They can probably cause you to have greater back conduction than you might think, but otherwise they help stir and cool the evaporator core, so it's hard to get too excited about them. Nonetheless, I think it's also important not to look at an LHP and say, oh, steady power, everything should be steady inside of it, right? Not so much. Again, a little dangerous to think of these things as a black box. Startup is a much more uncertain and controversial subject. So maybe I'm going to chicken out a little bit and not talk about it in too much detail, other than to say this is definitely an area you need to pay attention to, and it can have a lot of complexity in it. So all I'm trying to do right now is show you the kind of complexity that you may experience trying to get an LHP to start. Let's say you start out with that evaporator again. This time the bayonet's full, the arteries in the core are full, the vapor passages are full. So this is all cold liquid sitting here, and you start to apply heat to it. Now, ideally, you would like this vapor channel to bubble first, to nucleate first, but that may not happen. So it's really hard to get a gradient established between this hot side here and this cold side here when you go to very low power start. And of course, if you attach a large mass to an evaporator, and who wouldn't, then it can be very hard to get the heat, to get a gradient here to cause nucleation to happen first out here and not in the inside. So in other words, the heat will slowly soak back into the core and just heat it up again without causing that temperature gradient that you need to get the LHP going. In fact, it's a lot worse if it doesn't start in this condition. It actually starts with some vapor or two-phase on the inside. Now, if heat will go right past those vapor channels and start boiling on the wrong side of the wick. And it's very hard to get the temperature difference going enough to get the loop flowing in the right direction. So you got to get a temperature gradient across the wick to get it flowing. It's tough with large attached masses. Just because you think bubbles should happen here first doesn't mean it will. So please watch out for hopeful thinking, or thinking like that's how it's supposed to work, right? Well, bubbles will form, or bubbles want to form. That's scar tissue talking. So please be careful. One of the ways in which you can try to make sure that bubble forms on the outside and get that temperature gradient going is to put a start heater on the outside. So you're not just relying on slow soak back of energy from your cooled payload, but you're actually putting a point source of heat here to try to get it to nucleate on the outside first. Another trick is to cool the inside instead. So to get that delta T from here to here, instead of heating here, you can just cool here in the middle. So if we cool, remember that this is best off considered part of the condensation chamber. So if I were to cool the condensation chamber with a thermoelectric cooler, a Peltier element, I can also get a lower temperature and going here and cause the nucleation to happen like I would like it to be. So I think a way of thinking about this, if you're not quite hanging in there with what I'm saying, is think of an LHP. I told you to think of an LHP like a transistor. Now I'm asking you to think of it like an airplane with a stall speed. It basically likes to get going at high speed, but it's hard to take off and land. So low powers tend to be the trouble zone for an LHP to establish that delta T and get things moving. Again, in the interest of time, I'm going to skip over these more rare and uncommon startup concerns like the purge surge clearing out the vapor line, very high velocities of cold liquid rushing around through the system. It can exceed the capillary pressure limit, which is not immediate failure in an LHP. Just because you temporarily or transiently exceed the capillary pressure limit doesn't mean the LHP is dead. It just means that it's experienced some stress and may have bubbles on the wrong side and so forth. So just so you're aware that they're not that delicate. So I'm not going to cover these right now because we just don't have time, and they're not too common and not often a great concern. This cold shock issue of collapsing ullage inside a condensation chamber can happen, but it's as long as you're aware that it can happen, it won't trouble you. A little bit more interesting is gravity assist. I start off a slide here by saying, hey, gravity is assisting. How bad can it be, right? How can an assist hurt you? Well, there is kind of a subtle effect in that you're starting an evaporator with that flooded subcooled state that can lead to some interesting startup problems, but a lot more common is the fact that the gravity is so much stronger than the frictional resistance of the loop. It starts circulating at a much higher rate than you think it would. It's no longer really an LHP. It's actually more of a coffee percolator with very strong flow rate and pressure variations, very strong oscillations, very high flow rates. So the actual biggest risk of this is you just have to make sure that if you're going to test in a gravity assist condition, that you have provided enough heater power to not lose control of your set point. So this is an analytic example of a fairly low flow rate here when you're operating in horizontal condition. As an LHP, it's got a flow rate, you can probably barely see this, but a flow rate of 10 to the minus 4 kilograms per second, funny units. But when it's operating as a loop thermosiphon in a gravity assist mode, it's got 5 to 6 times more flow rate on average, and it's violently oscillating back and forth here. It's essentially bubbling and percolating, just so if you do have to withstand that sort of ground test orientation, make sure that you know that's going to come. The final subject I wanted to talk about was multiple LHPs in parallel, because that can also cause some things that people may not realize. And some of this results from the fact that people would love to have multiple evaporators on an LHP, but that's actually tough or risky, not very common. It's a lot easier to have a single evaporator and a single condensation chamber. Maybe in the future we'll have more variations. Maybe someone right now is wishing that they could unmute and scream that they've already solved this problem. But let's say for right now you can't. You have to have one evaporator, and for that reason, if you have a distributed heat source, you may need to use multiple LHPs rather than multiple evaporators. More commonly, you've got 2 LHP units in parallel for redundancy in case one gets punctured. And in that case, the evaporators are either co-located or are interconnected with the traditional heat pipe. The condensers are kind of interwoven so that they can replace each other. And the reason I want to mention this is you may not realize that something that happens in a case like this is that you get one unit starting and the other unit never starts. It sits there in an unstarted state, not flowing. Now, the reason is it's almost as if the unit that started first stole all the available superheat and got going, and the other one didn't get going. And it's also very easy for one unit to drift to a very high power and the other unit to drift to a low power, especially with a little bit of adverse tilt. But that also happens. Just because you have 2 LHPs in parallel, they will almost never carry the same amount of power. And that's not a huge design concern, because if the reason you were doing this was for redundancy in the first place, then you certainly want to make sure that one LHP can do the whole job anyway. It's just more if you had not expected this, either for test or verification, or you're trying to verify that both LHPs are actually alive and working, and one just won't start because the other one keeps stealing its energy. You just need to be aware that those kind of things can happen. So I know that it's been pretty easy if you've listened through all this to say, wow, there's a lot of strange things that can happen in an LHP. I'm now scared of them. That wasn't really the intention here. The intention was to have you go in with your eyes wide open about what can happen and how they work, and what kind of things you need to design against to succeed. So as a user of LHPs, and I'm sure that 95% of the people listening here are in the mode of actually buying or integrating an LHP rather than trying to design one, you need to understand some of these strange things that can happen and how to design against them and what's the worst case. And so you're not surprised when it's too late, when the thing's already sized and integrated and suddenly your test is not going like you expected it to go. If you're an LHP manufacturer, you need to understand why the person who's buying and integrating this can't really be sold and as a black box. It's very tempting if you have a lot of proprietary details inside of your device to say, no, that's our business. You just, what's on the outside of the metal is your business. What's on the inside of the metal is our business. Can't really work that way. You have to participate with some of the interesting things that can happen in here and help them design against them. And that's, of course, one of the major things we want to accomplish today is to try to help stress that knowledge gap. For more information on this, of course, we have 3 more webinars coming up. I would actually encourage you to wait and not look at our sample problems until you've gone through those classes. But if you can't wait, you're welcome to use these links here to jump over to some of the more detailed sample problems at system and detailed level modeling. There are some webinars already recorded on pipe and tank modeling methods, two-phase flow, and so forth that I think you'd probably be better off spending your time if you're not familiar with modeling these kinds of systems to learn those sort of things first before jumping over into LHPs, which is a much more specialized area. And then finally, we have some third-party links to third-party application, or I'm sorry, third-party papers, publications on our website here. If you look down at the bottom of your GoToWebinar control panel, you will see that handout that you can grab, pull down. If you're for some reason not successful in that, go ahead and send us a note and we'll get that to you. This will be recorded and is being recorded and will be placed on our website soon. I'm going to open this up to questions now. We've had some questions coming in. I'm having a little bit of a hard time seeing them.
There's one question from Stephen about the liquid flowing through the arteries of the secondary wick.
Right.
It might be worth mentioning it to other people.
Okay. And so the question is there a dead end at the end of the artery? And no, in general, that's open. It's open on one end to the bayonet flow and on the other end to the compensation chamber. I suppose you could put a dead end in there, but I don't think that's necessary or done.
Well, being open, it allows flushing of the vapor bubbles back into the compensation chamber.
Right, yeah. Let's just say I don't think I would do it, but maybe someone does it and disagrees with me. If you would like to ask a question without typing it down, please raise your electronic hand and we will unmute you. And you can ask it out loud. Otherwise, please type a question in there into your control panel. Let's see, can you model two-phase fluid-like bubbles inside the wick? Well, that's an interesting case. The question is, I think, inside the primary wick, what happens if there's some vapor and some liquid inside there? Can you model it? I think the best answer is we have kind of partial solutions to that. I wasn't talking a lot of modeling today, but I don't think I deal with that question in later classes. So one partial solution is there's a thing called a wick I-face, which helps you model the flexibility of a primed wick. That's more for fast time scale events. It's also possible to have kind of leakage paths. So if you want to model partial deprime, like during a startup event, you had a high stress period and you want to let vapor kind of sneak through onto the wrong side of the wick, you can do that. But otherwise, I think the most honest answer is no. It's not that easy to figure out what's going on inside the primary wick if you have both phases there. It doesn't move around like a bubble or a front or anything like that. They can form very complex shapes. Looks more like a crab or a cancer or something like that. Any other questions here, Jane? I don't know if you're seeing any.
Nope, I think that's it. There were some questions about charts and recordings. Recordings will be available on our website on our recorded videos page.
Okay.
And as you said earlier, charts can be downloaded from the handout area of the control panel for GoToWebinar.
Here's one on LHP working fluids. The same working fluid. I didn't really talk about working fluids. So question, actually 3 questions. Do they use the same working fluids as heat pipes, and can they use a mixture? And do they tolerate NCGs or non-condensable gases? So first question on working fluids. Yes, in general, they do use the same working fluids as heat pipes. For example, ammonia is used in both of them. I don't know that there's too many cryo heat pipes, but a cryo CPL or LHP would use something that you might not traditionally think of, like nitrogen or xenon or neon or something like that. I think the main difference on an LHP is because it has a significant subcooling, which is not typical in a heat pipe, and because the flow rate, the pressure losses are just not the same as in a heat pipe, they can get away with fluids that you may not want to use in a regular heat pipe. An example is like propylene. Propylene would not be a very good working fluid for a room temperature heat pipe, or at least there's better fluids available, so why use propylene? But propylene is actually not a bad choice for an LHP because even though it's got a much lower heat of vaporization, it also has a really low freezing point, so it allows you to have those nice cold sections inside an LHP without worrying about freezing. And I guess the last part of that question on non-condensable gases, well, they're definitely better than a constant conductance heat pipe, which is much more sensitive to gases. I don't know how it would compare to a variable conductance heat pipe because they both can tolerate some gas there. In an LHP, the non-condensable gas just ends up in the compensation chamber, and it'll shift the set point around. It might affect startup, so it's not like it's a good thing, but it's certainly not fatal, and I'm sure there's a fairly good limit it can tolerate of generation of NCG over the lifetime.
We do have a couple more questions.
Okay, yeah, coming in the meantime.
The first one, pardon?
Go ahead.
Oh, the first one is it is not clear how nucleation can start in the inner groove instead of the OD if heat flux is coming from the outside of the evaporator. Can you please explain that again?
Sure. So let me back up here in my charts. Sorry, there's probably an easier way to do this. Let me back over to that chart of the cross sections here. There we go. So your question is, I think, basically this here, that let's say this thing is full of liquid, and if this is the hottest temperature point, why isn't this also the place where nucleation happens first? And the answer to that is that for nucleation to start, you essentially already have to have a nucleation site present. So if it's not just a matter of it being the warmest spot, it's also the warmest spot with the biggest nucleation site. And it's fairly easy to have a bigger nucleation site here in a colder zone, especially when it's very hard to get a temperature gradient going here. So keep in mind, this isn't a very strong temperature gradient from the outside to the inside. So this might be a tenth of a degree warmer than the inside of the wick. And that may not be enough to overcome the fact that there's a bigger nucleation site, or potentially a bubble left over from the last time, or that crept in from the compensation chamber or something like that. So whether there's a prior bubble or a nucleation site left over, possibly inside the wick, not just at these zones, you have to have a certain amount of incipient superheat to get a nucleation site to grow, and it may not happen where you want. It may not happen when you want. It's possible to get several degrees of superheat going before liquid will finally convert over and start to boil. So I hope that answered that question.
And on that line too, people need to be aware that, while you're trying to develop that superheat, whatever your, components attached to that loop heat pipe could be seeing a temperature excursion. So they need to design for any potential temperature excursion during that period of developing superheat.
You have a big mass attached out here that's heating. So with very, gradual heat leak in here, it's very hard to get a gradient going across that. So like I say, it's almost as hot inside here as it is outside here. So it would take a bubble in the right spot or nucleation spot. And in fact, it's possible to have the loop start and operate, and this zone in here stay subcooled, and I'm sorry, superheated. Same thing in this. So you can actually have this loop start and operate, and this is actually where vapor is forming, not here. So unfortunately, it's one of those things where you have to not use wishful thinking about where a bubble should form. The darn things will form where they want to. Another question is an LHP the same thing as a CPL? Yeah, Jane and I both cut our teeth on CPLs back in the 80s. Sorry, Jane, I just let them know how old we both are. But the CPLs are slightly different in that the compensation chamber is separated into a reservoir, so it doesn't flow through it like it does in LHP, and there is no wick connection between them. So CPLs are still around, but LHPs have kind of taken over in a lot of ways, or at least they've hybridized so that it's a little bit hard to tell where a CPL ends and an LHP starts. But I think it's a fair statement to say that most things flying are now LHPs, and CPLs are still have a few hurdles to clear in acceptance. So no, they're not exactly the same thing.
Yeah,
they are very similar.
I'd say what we have today is sort of a hybrid of the two. There's actually we had posted a blog recently on our website if you're interested about sort of the history of CPLs and LHPs and how we got to where we are.
I had one last question here. I guess I failed to answer in that earlier one was, can an LHP handle a mixture? And I'm not quite sure what that question meant, but I think probably if you meant like a hydrocarbon mixture or a mixture like a non-azeotropic refrigerant that has different boiling points, no, that you really need to have a single substance, a single boiling point for it to work. If you had a mixture in there with some stuff with a high vapor pressure and some stuff with a low vapor pressure, then the stuff with the low vapor pressure would distill out, would separate out, and so the LHP would essentially become a separation column and separate into two substances again, and that would be the end of circulation. So no, I don't think you can use a mixture. Okay.
I don't see any other questions.
Very good. You have our contact information on the first page. So if you have any other questions, please write them in. And we will look forward to seeing you at the second webinar in the series, which is next Tuesday. Jane will be covering system level modeling.